Good. Thank you once again. This will be half-hour presentation of my doctoral dissertation titled Reduction Strategies in the Lambda Calculus and their Implementation through Derivable Abstract Machines. And as I usually do, I will start with explaining parts of the title. So we'll start with reduction strategies. And let's take something simple, an arithmetic expressions. Here we have a sum of two sums of natural numbers. And we can evaluate this expression in two ways. For example, we can start with evaluating 1 plus 2, and no wonder obtain 3. But we could also start with adding 4 and 8 and obtain 12 and obtain this intermediate form. In both cases, then we have to, if we want to proceed with the computation, we reduce the remaining sub-expression. We meet in the same intermediate form and obtain the same result. This is a simple example, but we can say that while computing this expression, we followed two different reduction strategies. The first was left to right reduction strategy, and the second was a right to left reduction strategy. Okay, but in case of additive expressions, this choice of reduction strategy doesn't matter much. So let's switch to something more involved. Let's consider functions. Let's take function whose value f of x is x plus x. And now let's compute the value of this function for product 3 times 7. If we would follow the strategy called call by name, we would just substitute the product to the expression, so the product, the operation to be executed, is duplicated. But we could follow also a call by value evaluation order and evaluate the product first, so then the number 21 is duplicated in the next step of computation. In case of this example, we can join call by value evaluation in 2 steps and obtain the same result. But as we can see, in both reduction strategies, there were different numbers of steps. In call by name, we had 4 steps of computation. In call by value, we had only 3 steps of computation. And this is my main motivation of studying reduction strategies, to save computational steps that are not needed to save our resources and similar things. And now, if we prefer to define functions themselves instead of defining their values, we can use another notation. We can define f as a function that takes x and returns x plus x. To define a function, we use the letter lambda, and hence the name Lambda Calculus, in which we work. The Lambda Calculus called one calculus of functions, and it was conceived by Alonzo Church nearly a century ago. It is a fundamental, foundational model of computation. And speaking about models of computation, we have to mention also a famous doctoral student of Alonzo Church, Alan Turing, that proposed another model of computation, nowadays known as Turing machines, that convinced multitudes that it is a notion of algorithm we agree that is correct. But also even Turing worked on Lambda Calculus, and it can be witnessed by a Lambda expression that he designed to calculate fixed points of other functions. And in this environment of cooperation of Church and Turing, from it comes also a Church-Turing thesis that first observes that the two models, Lambda Calculus and Turing machines, are equivalent in this sense that everything that is computable in Lambda Calculus is computable on Turing machines, and vice versa. And going further, it turns out that these models are equivalent in the sense also to other models proposed as a definition of algorithm, of Gödel's, of Post's, of Markov's, of Kolmogorov's. So this gives us a feeling that computability, that algorithms are nowadays well-defined notions. And in 1960s, Peter Landin made it evident that Lambda Calculus can be used also as a programming language. And in my view, it is much more convenient to programming than programming Turing machines. You can try and, and experience this difference. And this language is so powerful that I wanted to study it and experience what can be made with it, how many applications can we find. Okay, so having said that, let's take a look at what's coming next. Throughout the rest of the talk, I will present the main contents of the technical chapters of the dissertation that are research papers published with my co-authors. And to explain much of the context, we have also to introduce the notions, or at least intuitions, of abstract machines. Then I will talk about functional correspondence as a tool to derive abstract machines. I will also say a word about improving efficiency of abstract machines, and I will add some methodological remarks. Okay, so the first technical chapter is the zoo of Lambda Calculus reduction strategies that has been mechanized and verified in Coq system, in Coq proof assistant. And this is the picture that summarizes the most important, in a sense, you are most interested in properties of these strategies. In the picture, we can see CBN and CBV that stand for call by name and call by value. And here we have also 22 another reduction strategies that we systematized a bit in this picture and verified that everything we claim in this picture is true, checked by computer. And the particular focus of this study were strong reduction strategies, or strong reduction itself. And to show what it is, let's take another example. Let's try to evaluate this lambda expression with call by value strategy. On the right-hand side, we have an argument, so we have to evaluate it first. It is lambda ZZ applied to lambda WW. So we substitute the lambda W for Z and obtain itself. And now it is a lambda function. It can be treated as a value. So we can substitute it for X, and we obtain the following form. In conventional functional programming languages, it is enough for computation to flow, but under the lambda, we see that there is still a function, lambda ww, applied to a variable y. And so-called weak reduction stops here because we've reached the lambda function, we've reached so-called weak normal form, and doesn't go there. But we are interested in also in full normal forms where no reducible sub-expressions are present. And to obtain them, we have to switch to strong reduction. And for example, we can extend this weak call-by-value strategy to strong call-by-value strategy. So we finally obtain this result, lambda y, y. And it is full normal form. And we are particularly interested in this because they find an application in type checkers, in proof assistants such as Coq, but also recently it was discovered that strong reduction is applicable in OCaml compiler. Okay, and now the remaining 3 technical chapters of the paper have abstract machines in their titles, so it's time to introduce them. What we expect from the abstract machines is that they are finite state machines, and then they can work on potentially unbounded data. So first we can think of Turing machine. A configuration of Turing machine consists of this potentially unbounded tape, but in every cell of the tape, we have a finite amount of information. And the same is for head that moves above the tape. The head also, in the single point of time, looks in the single cell and stores a finite amount of information in itself. And despite the simplicity of this model and all the constraints that it has to be finite there and finite there, this model, Turing machines, is capable of any computation. And what I like about abstract machines, and it's their finitude, is that we can reflect upon our own finitude, but more technically, they also give a natural, simple, and realistic cost model for computations because a single step of computation can be, comparing to RAM model, executed in constant time. So the cost model is really realistic. And we use abstract machines as tools to measure this complexity of also other programming theoretical constructions. Okay, and an analog of the tape in our abstract machines will be the syntax tree of the expression that is evaluated, and it is a graph. We can annotate every node of this graph with value of sub-expression. So this graph has 7 nodes, and what interests us more in this case is that we look at the particular place in the syntax tree. So we can move to the sub-expression 1 plus 2, and now we focused on this sub-expression 1 plus 2, and we are in the context whole plus 4 plus 8. So this whole shows where is the place of the focused expressions to be plug the back and to recompose whole expression. So we can retrieve the information what the whole expression is and where we are in it. And we represent contexts as a list of frames, as a stacks of frames. So if we move to the 1, we add to the stack another context frame that is whole plus 2. We can also move to the 2, and then we have the frame 1 plus whole. So the 2 should be plugged in the whole, and we have then the whole expression. Okay, and to ease reading and writing, we applied also in one of the chapters refocusing notation. So instead of showing the focused expression and its context separately, we put them together again, and we just mark the focused expression with angular brackets. So I hope it is more visible, and we can play with this notation to move the focus over the expression and show a bit more precisely how this computation proceeds. But still, it is not this mechanical precision that is about to come. So let's turn to an abstract machine that will evaluate additive expressions of integers in left-to-right strategy. A configuration of such a machine will consist of the focused expression, what we've just seen, the stack of frames that represents the reduction contexts, and a direction tag that informs if we want to evaluate the focused expression or if the focused expression is already evaluated and we want to just recompose the result. And having this configuration, we can see that in this focused expression, we have two unevaluated expressions. So going left to right, we start with evaluating the left sub-expression and put the right frame on the stack. And we proceed with an arrow downwards because we evaluate E1. In case we reach a number itself, it is a value, so we just switch the tag upwards. And now, in case of recomposition, if we encounter an evaluated expression on the stack, we switch to its evaluation and put the evaluated frame on the stack as a left frame. And if the left frame is also already evaluated, we perform the addition of the two numbers. So it is not longer represented as a sum, but we do this sum at the meta level. So the numbers are replaced by their sum. And it is enough to evaluate arithmetical expressions with only addition. And we can follow how the evaluation proceeds. We put the direction tag as a subscript of this angular bracket. So such a text represents the whole composed of two sub-expressions. We go to the left sub-expression again. It is then recognized as a value. We go up. We switch to the 2. It is recognized as a value. And now we, on the stack, left frame with evaluated 1 is present. So we can perform the addition, and the two numbers are replaced by 3. And with some other steps, we can reach this value 15. OK, so this is the abstract machine that is the main result of the second technical chapter. It is the first in literature abstract machine for strong call by value. And as you can see, it is a bit more complex than the abstract machine for arithmetic expressions. It also has to perform search of the place where the reduction will be performed. But also it has to deal with substitution because we work in world of functions. It has to reduce under lambdas, under binders, because it performs strong reduction. And it has also somehow avoid to conflicts of names. So there are much more to provide in this case. And designing such a machine by hand would be, in our opinion, quite hard and error-prone. And what can be done is to apply functional correspondence. And going back to arithmetical expressions, let's express them as a data type. The additive expressions are constants of, in this case, integer numbers, or sums of two expressions. And their values we expect are integers. Evaluation function is a function that turns expressions into values. And if we encounter a constant, we just return this number. In case we encounter a sum of two expressions, we evaluate both of them and add them. And that's all. We can also reify back a value to expression. So the whole process can be called normalization because we can obtain this way an expression that has a canonical expression that has the same value as the input. And the normalization is just the composition of evaluation and reification. And having that simple program, we can do so-called CPS translation of the program, and then apply another program transformation, that is the functionalization. And what we can see in this code that we just obtain as an output are these four clauses of pattern matching that directly correspond to the abstract machine for arithmetical expressions that we've just seen. And we just derived it from the intuitive program with no design phase for direction tags, because, for example, they are reflected by eval and cont in this mutually defined recursive functions. And okay, let's take a look at this process again from the perspective. We started with normalization by evaluation function. We applied CPS translation and the functionalization. And such a process was described in 1972 by John C. Reynolds. And his focus was to make definitional interpreters unambiguous. So we can unambiguously define programming languages by such interpreters, CPS translated and defunctionalized. But in 2003, Dundee and his then doctoral students observed and showcased that this process is process of constructing an abstract machine. And we can follow abstract machines from the literature that can be really derived from functional programs. And moreover, abstract machine, this process can be reversed, so we can deconstruct abstract machines, and in terms of programming, we can see what's inside. And the first look, the normalizer for strong call by value could look intimidating too, but it consists of many standard parts. It has in a relation with strong call by name normalizer. So this process can be approached much more easily, in our view, from this point. But the abstract machine we obtain this way suffers from exponential overhead. And if we want to save time and resources, it's not that good. And the problem is that in n steps of reduction, the term can grow exponentially in terms of the number of reduction steps. And since the abstract machine we obtained builds every node of the syntax tree in separate steps, it does exponentially many steps and hence the overhead. So in the next technical chapter, we can see how it can be improved. And we apply another standard programming technique, that is memorization. So instead of calling f of x, we can have a dedicated memory cells that once the value is computed, it is reused every time it is needed again. And this leads us to implicit sharing of sub-expressions. But thanks to that, the exponentially big expression can be represented as a linearly big structure in memory or on the paper. But to prove that this machine is really free of the exponential overhead, we had to apply amortized analysis of time complexity. So the chapter provides a potential function a la Chris Okazaki that treats the configuration of abstract machine as a persistent data structure and bounds how many steps the machine can make without performing the reduction in the calculus that we represent. And the potential decreases in every but one transitions. It can only increase in the transition that has to take place before the reduction in calculus occur. But then the potential cannot grow more than the potential of the input term, and this bounds the number of execution steps in the whole process. And we can also empirically trace how this potential changes over time. So in this case, we had 8 reductions, but only 5 of them increased the potential, and then the machine discharged its potential and returned normal form. And the last technical chapter is about an abstract machine for strong call by need. That is a first asymptotically efficient abstract machine for the strategy, and unexpectedly it is less complex than machines from previous chapters. It also uses memorization on the 2 levels, on the weak level and on the strong level. And analogously, the techniques from previous chapters are refined to obtain this result. And what more, every chapter is accompanied with code that is publicly available. And having this code, we can run these computations, we can measure how many steps machine take to obtain the normal form, how many reduction steps this strategy in the Lambda calculus does. And I believe that it helps reproduction of the results. It can also helps to test our hypothesis faster, to reject machines that have exponential overhead and work more to obtain machines that are efficient. And with this slide, I wanted to underline again the synergy between programming and theoretical research, because we have seen the program transformations, memorization, and use of implementations to obtain theoretical results. And I hope that it will help many people to enjoy similar experiences. For now, that's all from me. Here is the summary of the technical chapters, and I'm happy to hear your comments and questions. Thank you for your attention.